This question is on calculating the coherence time of a laser. So this is exercise 2.5. It says calculate the coherence time for the 589.0 nanometer line of a sodium lamp. Coherence time of a sodium lamp we want to find, not of laser. Coherence time of sodium lamp operating at 100 degrees centigrade in the following two cases. A, the line is Doppler broadened. There are various broadening mechanisms. So one of them is Doppler broadening. Another broadening mechanism is pressure broadening. So the line is pressure broadened. With a full width at half maximum of 5 gigahertz. So this is a simple question. It is basically a formula based question. So let us solve it. It's a formula based numerical. So for A, the Doppler broadening, in the case of Doppler broadening, so in Doppler broadening we have the spectral width, the frequency width, given as follows. This is the spectral width for the case of Doppler broadening. Over here, lambda is the wavelength. In our case, the wavelength is 589 nanometers. Then we have KB, which is the Boltzmann constant. The value being 1.38 into 10 to the power minus 23 meter squared kg per second squared Kelvin. So this is Boltzmann constant. T is the temperature in Kelvin. Temperature in Kelvin. So in our case that would be 373 Kelvin, which is same as 100 degrees centigrade. M is mass of atom, and the atom in our case is sodium. So mass of sodium atom is roughly 23 grams per mole. So we can find out the mass of one atom, because 1 mole, so 1 mole means Na, that is Avogadro number of atoms are there in 1 mole. And for 1 mole, that is 1 Avogadro number being 6.022 into 10 to the power 23. For these many atoms, the weight would be 23 grams. So we can find out not the weight, the mass would be 23 grams. So for one atom we can find out the mass, how much mass would be there. So this is the spectral width. So delta omega is the spectral width of the particular line that we want, and from this delta omega we will get the coherence time. Coherence time tau c as follows. This is given by square root 8 pi log 2 over delta omega. This is for a Gaussian line shape. So Doppler broadened and Gaussian line shape, for such a case we get tau c. Tau c is coherence time. So plugging in all these values that we have gives us tau c roughly of the value 4.5 into 10 to the power minus 10 seconds. So this is for the first case. We just plug in the values, these values for lambda, kb and p and m in Tm over here to get spectral width. Then using that spectral width we can put it in this expression to get coherence time. Next part is for pressure broadening. Pressure broadening. So in the case of pressure broadening, we have been given that the full width at half maximum is 5 gigahertz. This is nothing but the frequency width. So if this is the frequency width, then the spectral bandwidth would just be 2 pi times delta nu. So this would give us this is coming because omega is 2 pi times nu. So d omega is 2 pi times d nu. So you get delta omega is 2 pi times delta nu. Now in this case tau c by definition of coherence time is 1 over this delta omega. So plugging in the values over here, we have delta nu equal to 5 gigahertz. So if you put in 5 gigahertz multiplied by 2 pi, we get delta omega. If we take the reciprocal, we get tau c, which is coherence time. Just putting in the values in the calculator, we get the following. So this is coherence time for the pressure broadening case. So this solves us this question. It was for finding coherence time of the sodium vapor lamp, one line of that sodium vapor lamp, and for two different cases we calculated the coherence time. The first one for Doppler broadening case and the second one was for pressure broadening case.